Welcome to the class. We are talking about axial compressor. Today's discussion will be focused upon free vortex condition in the design of axial compressor. So let us see what does it mean by free vortex condition for the design of axial compressor. Actually, when a fluid element is passing from the compressor, we know that this is a schematic of axial compressor, this is the shaft, and first the fluid element will go from a rotor and then it will go from the stator. So this is rotor, this is stator, and then these rotors and stators are arranged in series. So in this case we are having flow in axial direction for the air, and this air is experiencing two motions. One is the rotational motion in the presence of the rotor blades. So there is rotational motion in the presence of rotor blades, and then there is axial motion of the fluid particle. So these are two motions experienced by the fluid particle. Let us consider radial equilibrium and condition for radial equilibrium. Here let us feel that there is a fluid particle of a particular shape which we are drawing now. This is the fluid particle, and then this fluid particle is flowing this fluid particle is passing from the compressor in this manner. So this fluid particle is going along a streamline. So this is streamline in a steady flow, and then but this fluid particle is also rotating along with the rotor. So this is the rotational direction. So let us consider the geometrical dimensions. Let this be dr, since this is along the radius of the compressor, and then this is the r radius of the compressor, and then there will be the streamline which is having curvature, and that streamline has its own radius, and then that radius we are denoting by RS, streamline's radius. So this we are denoting by RS. Now fluid is flowing with axial velocity, and then it has radial velocity CR, and then this is the velocity which is tangent to the streamline, and this is CS which is making angle alpha with axial velocity, and then there will be fluid element which is moving in this direction with velocity CW. So for the pressures which are acting upon the fluid element, let us consider that the pressure acting on this surface is dP, pressure acting on this surface is acting on the bottom surface is P, on top surface is P plus dP, and on side surfaces the pressure which is acting is P plus dP by 2. Let the angle between the two faces is d theta. From the geometry, dw is the width of the fluid element. Now we are drawn the free body diagram of the fluid element, and now we will consider different accelerations and the forces which are acting upon the fluid element. So first we will consider acceleration, which is suppose x1, and that is due to the centripetal force, and that acceleration is in the presence of velocity cw. So this is m cw square divided by r. This is due to the rotational motion along with the rotor. Now we can find out m, which is mass, which is density, into delta v, which is volume, into cw square divided by r. But we can further write down volume as r d theta into dr into dw into cw square divided by r. So this is the first acceleration in the presence of rotational motion. Second acceleration is due to the curvature of the streamline, and then that acceleration is m into cs square sin alpha, cs square rather cos alpha, since it is the direction of velocity, cs square sin cos alpha divided by rs, which is the radius of the curvature of the streamline. So this is again rho dv cs square cos alpha divided by rs, and this gives us rho r d theta dr dw cs square cos alpha divided by rs. Now there is third acceleration for the fluid element, and that acceleration is due to change in velocity with respect to time, and that is dcs by dt into sin alpha s. We are talking about radial equilibrium, so this acceleration is in the radial direction. So we again can have rho dv into dcs by dt into sin alpha s. So we have x3 is equal to rho r d theta into dr into dw into dcs by dt into sin alpha s. Now these are the accelerations. Let us consider the force, which is F, and that force is prominently due to pressure. So consider pressure forces acting on the fluid element. So for the top surface we have force which is P plus dP into R plus dr into d theta into dw, while for the bottom P into r d theta into dw, and for the side forces the pressure force will be 2 into P plus dP by 2 into dr into d theta by 2 into dw. If we expand this and neglect the higher order terms, we can write F is equal to dP into r d theta into dw. Only one term would remain, which would be this term. Hence this term can be written as dP by dr into dr into r d theta into dw. So we have one acceleration x1 due to the tangential velocity, acceleration 2 due to the curvature of streamline, acceleration 3 due to the unsteadiness in the flow or the time varying Cs velocity, and then we have acceleration, we have force which is due to the pressure. Now let us equate this and we can see that F is equal to x1 plus x2 plus x3. So we have dP by dr into r d theta into dw is equal to, we can take mass which is common, which is rho r d theta dr dw, and all the terms related to velocity will be inside the bracket. So first will be for the tangential velocity of the fluid element, second is curvature term for the streamline which is Cs square cos alpha s, and third term is dCs by dt into sin alpha s. Now this term gets cancelled, so we will have dP on the rho would remain, so that will be rho into dP by dr is equal to Cw square divided by r plus Cs square divided by Rs cos alpha s plus dCs by dt into sin alpha s. Now let us make certain assumptions. First assumption here is that Rs is very large, so Cs square divided by Rs into cos alpha s is equal to or close to equal to 0. Second assumption is alpha s is very small, and this makes dCs by dt into sin alpha s which is very small, and then that would go to 0. So having these assumptions made, we can write down dP by dr into 1 upon rho is equal to Cw square divided by r, or dP by dr is equal to rho Cw square divided by r. We will mention it as equation number 5. Having said this, now this was from the momentum equation. Let us get another expression from the thermodynamics which states that H naught is the total enthalpy of the fluid element, and that is equal to H plus C square by 2, and then this is H plus C square can be further decomposed into Ca square plus Cw square plus Cr square by 2. Now here Cr is very low in comparison with Ca and Cw, so we can write H naught is equal to H plus Ca square plus Cw square divided by 2. So variation of H naught with respect to R is dH naught by dr, that can be said as dH by dr plus Ca into dCa by dr plus Cw into dCw by dr. Further, we know that second law of thermodynamics and first law mixed together tells that Tds is equal to dH minus Vdp or dH minus dP by rho. So dH, we can represent this as equation number of 6. So dH is equal to TdS plus dP by rho. dH by dr can be written as ds into dt by dr plus T into ds by dr plus 1 upon rho dP by dr minus 1 upon rho square into dP into d rho by dr. So we can neglect the higher order terms, and then this term and this term would get cancelled, and we will have dH by dr is equal to T into ds by dr plus 1 upon rho dP by dr. However, from equation number 5, we can write down dH by dr is equal to TdS by dr plus rho Cw square by r. Hence, we can put this into equation number 6, and we can write down equation number 6 as dH naught by dr is equal to dH by dr plus Ca into dCa by dr plus Cw into dCw by dr. So dH naught by dr is equal to T into ds by dr plus 1 upon rho dP by dr plus Ca into dCa by dr plus Cw into dCw by dr. Here we will consider ds by dr is close to 0, which means that entropy is constant along the radius. This term would become prominent in case of compressible flows, where shock is going to appear prominently. So ds by dr is going to be 0 otherwise. Further, we will also say that dCa by dr is equal to 0, since we have assumption that Ca is constant at various heights of the blade. So we have dH naught by dr is equal to 1 upon rho dP by dr plus Cw into dCw by dr. Further, we can write down for the dP by dr as dH naught by dr is equal to 1 upon rho into rho Cw square by r plus Cw into dCw by dr. So we have Cw square by r plus Cw into dCw by dr. Now this is our equation. We will number this as equation number 7. In this equation number 7, we have left hand side which says that dH naught by dr, and we have right hand side which has terms related to velocity. This left hand side term says that variation of H naught with respect to r. That means this term is related with absorption of work at various radius of axial compressor. Now we assume that we have designed axial compressor such that absorption is uniform. So dH naught by dr is equal to 0. So with this assumption we can write down Cw square divided by R plus Cw into dCw by dr is equal to 0. So we have Cw by R is minus is equal to dCw by dr, which is minus dr by R is equal to dCw by Cw, and which says that Cw into R is equal to constant. Upon integration we would get this Cw into R as a constant, and this is called as free vortex condition. If in the axial compressor Cw into R is constant at different radii, then it is called as free vortex condition. We should remember again that in the axial compressor, if this is the compressor, this is the shaft and this is the rotor. So for the rotor blade we have always considered that we are working at the mean height. So we can work at any height, it corresponds to any radius, but our all derivations till time for the pressure rise, for stage temperature rise were related to the velocity triangle drawn at mean height. But if we try to plot velocity triangles at different heights with the constraint of free vortex condition, then we will have Cw into R as constant. So we will see its repercussion. It says that Cw into R as constant. So let us see R lambda as degree of reaction, and we have derived a relation which says that 1 minus Ca upon twice u into tan alpha 2 plus tan alpha 1. So lambda is equal to 1 minus 1 upon twice u Ca tan alpha 2 plus Ca tan alpha 1. This from the velocity triangle we can write down as Cw1 plus Cw2 for the terms in the bracket. Let us multiply and divide by R such that we will have twice ur and then we will have Cw1 into R plus Cw2 into R, but Cw into R is constant, so we have 1 minus constant divided by twice u into R. So this is u velocity at some radius R. So this u is at some R, and we know it is equal to pi into twice R into n divided by 60, and this we can represent if we know u mean, which is the mean radius, the mean blade speed at mean radius, which is pi twice Rm into n divided by 60. Let us divide both the terms. Then we have u at any R divided by um at Rm is equal to R divided by Rm. So we can have u at any R is equal to into R divided by Rm. We will put it in the expression of lambda, and we can get constant divided by 2 into into R divided by Rm into r. So this here mean radius and mean blade speed would be constant. So 1 minus that constant will get further strengthened and we will have only r square. So this expression says that lambda is equal to 1 minus constant divided by r square. So if r increases, that means if the location from the blade root increases, then degree of reaction increases for the axial compressor which is designed with free vortex principle. So this is how we would work for the design of axial compressor and then associated derivations. So here we have seen in all that how to find out the velocity triangles, what is the variation of different thermodynamic and fluid dynamic parameters along the axial compressor, what are the different components of an axial compressor. We derived for stage temperature rise, we derived for pressure ratio, we derived for degree of reaction, and then for the constraint of free vortex condition. We will see next topics in the next class. Thank you.